So good morning, good afternoon, good evening, wherever you are, and welcome to the Matrix Online seminar. And today we're very pleased to have Miranda Cheng from the University of Amsterdam present the September seminar. So Miranda is a Taiwanese born and currently in Taiwan due to the pandemic, a Dutch educated mathematician and theoretical physicist at the University of Amsterdam. And Miranda is famous for formulating the umbral moonshine conjectures and for her work on the connection between K3 surfaces and string theory. And we're very pleased to have her here today to talk about modular forms and applications. Before we start, I'd like to advertise upcoming Matrix Online seminars. In October, we have Australian fields medalist Akshay Venkatesh. In November, we have Professor Peter Buhlmann from ETH Zurich. And then in December, we have Javier Torbo from CTO of his Google Cloud to talk about maths in industry. So one word on the house rules. We take questions at the very end. You can ask your question through the Q&A function at the bottom of your Zoom screen. And not via chat, but via the Q&A function. I hope you enjoyed today's talk, and I just want to hand over now to Miranda.
Okay, so let me first share my screen. I hope that's visible now. And thank you very much, Young, for the very kind introduction, and thanks to the organizers for the opportunity to give this online colloquium. And the topic of my talk is modular forms and applications. And before we start to talk about modular forms, let's just talk about something simpler, namely Q-series. Okay, wait a second. Of course, it has never happened before, and this is the first time, and my computer program crashed. So I gotta actually, my whole computer has crashed for mysterious reasons. Okay, now it seems to be coming back. So let's hope that this is gonna go on normal for the rest of the time. So Q-series, and in particular, I'll be interested in infinite Q-series because this is one of the things that a modular form is. So let's take a rather random looking example. So the example of a partition. So given a natural number, we can ask for the following question, namely, how many ways there is to partition this number n, okay? And this number is then called the partition number, P of n. For instance, when n is 4, as you can see here, there are 5 ways to partition the number 4. And there are 7 ways to partition the number 5, and so on. And in fact, Ramanujan has made this very interesting observation, which is the infinite sequence of partition numbers actually satisfy a congruence relation, namely, for all numbers that is equal to 4 mod 5, for instance this, its partition number is actually 0 mod 5. And similarly for 5, okay? And so on. And in fact, there are more of such congruences, and then they are actually tied to the modularity property, as we will see later, and more congruences can be read in the papers by, for instance, Ken Ono. That's much later, of course, than Ramanujan's time. Okay, so then in this context, then it's natural to consider a generating function for this infinite sequence. Namely, we make an infinite Q series in this way. So as we have seen before, it has the Fourier coefficient 1 plus Q squared, and 5Q to the 4th, and 7Q to the 5th, and so on. And as was proven by Euler, this actually can be written as an infinite product. Okay, nice. And well, what's not manifest from this definition in terms of generating function is that this is actually a function, not just a formal power series that's defined in the unit disk, okay? Or if we use another variable, let's call it tau, sometimes it's also called z, then this is mapped to the upper half plane. So the imaginary of tau will be always larger than 0. That's mapped to the in unit disk. And then there is a second property that is even less obvious. Namely, if you change this generating function for a little bit by multiplying an overall rational power Q in this way, okay, then what will happen, and then you call this function 1 of eta of tau, since I already said that this is a function defined on the upper half plane. Okay, then this function eta of tau defined on the upper half plane has the following modular property. So this is e to the 2 pi 5 over 24, if you're wondering. Okay, so this, how does it work? Okay, so this shows that, well, this function has a lot of symmetries, because let's look at the symmetries of upper half plane. And look at these two transformations. We call this the T transformation mapping tau to tau plus 1. So for instance, mapping this line to this line. And the S transformation mapping tau to minus 1 over tau. Then they actually generate an action of SO2Z. Okay, what is that? We know that the upper half plane has symmetries given by SO2R acting in the following way. If we write an element in this way, then it maps tau to gamma tau, which is A tau plus B divided by C tau plus D, and it's obvious to see that such an action preserves the upper half plane. And we often care about the discrete subgroup SO2Z, which is then generated by this T and S transformation. So looking back at the example, we see that this is invariant up to a simple function of tau under the SO2Z transformation. Okay, so that leads to the definition of modular forms. So in order to write down the definition, let's say a half integer, and gamma is an element of, let's say, SO2Z, and the function on the upper half plane, and then we define the modular transformation action, which maps this function to another function, which is defined to be, there's a weight factor if you want, and then you simply replace the argument by the transformed argument in the upper plane. So after defining this modular transformation, then the modular form of weight k, which is the same k, and for, let's say, a subgroup of SO2Z is a function that is, first of all, holomorphic, and second, has modular symmetry, namely it's invariant under the action we just defined for all element gamma. Okay, so the function simply has to satisfy these two things. And well, that's the plain vanilla definition, and there are many quite obvious generalizations. For instance, we can allow for exponential growth on the boundary of the upper plane, namely on the cusps. Oh. Okay, so that's called weakly holomorphic, and we can consider functions that's vector valued, let's say, and we can add some character in the transformation such that, so that means we have a homomorphism of gamma, and then this will show up here. Yes. Okay, so for instance, the example of the partition function will fall into this category. You need to add a non-trivial characteristic character to accommodate. So that's the definition of the modular form. So what are the nice examples apart from the partition function? Well, a super nice example is simply you raise the data king eta function that we just saw to the 24th power. Okay, and this will turn out to be a modular form of weight 12. And modular properties will bring with itself lots of nice additional properties. In this case, let's call the nth coefficient of this function tau of n. And again, as observed by Ramanujan, this tau of n satisfy the multiplicative condition, which says that tau of n times tau of m is the same as tau of m times n if the GCD of n and m is 1. So such a property will turn out to be a universal property for some type of modular forms, the Hecke eigenforms to be more specific. And the second place where this shows up a lot is, for instance, in the context of vertex operator algebra characters. So oftentimes, for instance, whenever your VOA is a rational VOA, then the characters of its modules will display modular, will be modular forms. And well, example, if I keep recycling this eta function, because that's convenient and that's pretty, this, okay, sorry. This function 1 over eta is actually, if you want, the character of what's called the Heisenberg algebra. Okay, some more examples. It also shows up in the context of, let's say, topology. As Jan mentioned, well, so K3 surfaces, which are, well, there are different ways to characterize them, but I would say they're the simplest non-trivial Calabi-Yaos. They're kind of my friends. So we can consider a variety that's the Hilbert scheme of m points on K3. Okay, and then you can take the Euler characteristic of it, and you might want to make a generating function for this. As we have seen before, you can make a generating function, and it turns out, again, recycling the theta function, that this is simply 1 over this way 12 modular form that we have just seen. Okay, so that's some examples where modular forms show up in different corners of mathematics. And now another example, which is in some sense the simplest example, because now there's no additional factors, nothing. You want to have function that is simply invariant under SO2Z under the modular group. And again, you want this function to be holomorphic on the upper half plane, inside the upper half plane. And it turns out that the space of such functions is rather limited, okay? And actually, the function I'm going to write down will be a generator of such a space. So in particular, to specify this function, you only need to specify how it behaves at the boundary, let's say at I infinity or equivalently q to 0, going to 0. Okay, we said that there is a pole, there is a singularity of this type, and then 0, and then whatever it is. Okay, so this is if you require the modular invariance and this behavior at I infinity, you actually uniquely fix this function. So that's, in some sense, a very simple example of a modular form. And it's also kind of fun because let's look at what these coefficients are. So these coefficients are some numbers. It grows quite fast. Well, I don't want to write down the next digit because it gets longer and longer, but these 2 is sufficient, or 3 is sufficient to make a point. So 1 is 1, and this is 1 plus 196,883. That seems to be a true fact. And then if I want to get this, I add them again. So, and now what? Now the point is that these are actually the dimensions of the 3 smallest irreducible representations of the monster group, okay, which is a finite group. So what is this group? Because, okay, the smallest ERAP is the trivial representation of dimension 1, but it's quite amazing that the smallest non-trivial representation already has like this 200,000 dimensions. So what is this monstrous object? So let's record that there are 26 sporadic simple finite groups. So finite simple groups that do not fall into any of the other infinite families. And the largest one has astronomical number of elements. And it's so huge that it's called the monster. So its existence backs the question, what does such a ginormous group naturally act on? So this question is actually, let's say, partially answered by what's called the monstrous moonshine. Okay, so among other things, it says that there is a vertex operator algebra, V natural, which is Z graded, and such that okay, it's sleeping again, sleeping again. I don't know what to do. Well, maybe I just, for now, before it wakes up or something, I just say such that the automorphism group of this VOA is the monster group. And moreover, the J function that we have seen before is the generating function for the dimensions of each of the homogeneous component. So this B natural sub n. Okay. So okay, it seems to be doing something again. Sorry for the technical issue. Somehow it never happens unless I'm giving a talk. It's always like this. So we have seen the definition. Oh, that's no good at all. Second. Let's see how we solve this issue. Well, can you see my screen again? Yeah?
Yes, we can. Yeah.
Great, thank you. So I'll just go on like this, and if the issue arises one more time, then I'll find some other solution, which is completely possible. I've got a backup plan, but let's now assume that it's never going to happen again for the rest of the talk. So we have seen the definition of modular forms, and of course we all know that it's a crucial part of number theory and has played an important role in, let's say, arithmetic geometry, for instance, and proving Fermat's last theorem and so on. But we have also just seen now that it plays a role in combinatorics and in mathematical physics and topology, and has nice interplay and crucially to and give great insight into finite group representation theory. So then the next topic would be, okay, so Mach modular forms generalize modular forms. So, and what are they and where do they appear? Is it like modular forms that they hold the secrets of many objects in mathematics, or what do we know and what we still need to know? Okay, so now let's move on. So a bit of history. The term Mach theta functions first appear in the letters of Ramanujan, and for instance, here you can see a letter to Hardy where he scribbled some, examples of Mach theta functions, as you could see his handwriting here. So So let's look at some of them. That gives a first way to think about what modular forms can be, sometimes are. So they were first written down as Q hypergeometric series. I'll give maybe 2 examples of what Ramanujan wrote down. So this example, Q and 1 minus Q squared and Q fourth. And in general, it is one minus Q2 and Q n squared. Super easy. And its coefficient is coefficients are ridiculously sort of simple and nice. Okay, so that's one example. And the other example of very similar flavor, Q n squared, again, 1 plus Q plus n, whole thing squared. Okay. And again, very simple Fourier development. So there are properties of these 2 functions and other functions that Ramanujan wrote down as integral coefficients. And coefficients grow very, very slowly. And the third crucial one that has been the missing piece for a long time is the modularity. So what does it mean? So Ramanujan wrote down examples without any kind of definition. And such a definition was then finally found by Sander Schwefers almost a century ago in 2002. So this is a definition of modular forms. Okay. So before that, let me tell you what's one thing. Okay, we know that some of you might know the Eichler integral of modular forms are kind of natural and important objects in the study of modular forms, and we can define similarly a non-holomorphic version of integral. So it maps modular form to what I write as here I was the Eichler integral. So you define another function. Well, given the modular form, that's your G, and then you map it to another function on the upper half plane. Okay, G star, which is literally an integral of this modular form. And what is interesting is that this G star will no longer be holomorphic. For instance, there's manifest non-holomorphic dependence on your variable here. Okay, so then going to the definition of modular forms, it says that a function is a modular form if the first thing the same as in modular form case, that it has to be a holomorphic function. And the second thing is that if there is a modular form, okay, that's what we call the shadow of F, such that we can write down another function F hat, okay, and then the F hat is going to be the thing that transforms just like a modular form. And the definition of F hat is simply F, and with the G star function, the non-holomorphic Eichler integral of G subtracted from F. Okay, so this is a funny, there are 2 ways to look at it, from the point of view of F and from the point of view of this accompanying function F hat, sometimes called the completion of F. So F is holomorphic, but it does not have any modularity property, but it can be completed into a function F hat, but F hat does not have holomorphicity anymore because of this G star piece. However, it transforms just like a modular form. Okay, so that's the definition, and sometimes F hat is called harmonic mass. Well, it is always in harmonic mass form, depending on. But just, depending on which perspective you prefer is more convenient for you, then you stress different aspects of things. Okay, so that's a definition, and we have seen already some examples given by the hypergeometric functions, and let's now look at the second example. And let's go back to the partition problem. And we define now also a rank of a partition, which is defined as the biggest part of the partition and subtract from it the number of parts, okay? So for instance, for the partition that 4 is just 4, and the rank is, the biggest part is 4, and the number of parts is simply 1, so the rank is 3. So then we can define a different partition number. So instead of just counting the number of partitions of n, we can count it with signs, and depending on whether the rank is even or odd. Okay, so for instance, well, P of 4 is 5 because there are 5 of them, and there are 4 of them with odd rank, and there's one of them with even rank. So that's why this signed partition of 4 is -3. Okay, you get the idea. And before we remember that's P of n and Q of n and minus this power, this is a modular form. And now let's look at the case with the signed partition. And it turns out that this is actually one of the hypergeometric guys that we have seen from Ramanujan's letters with this nice expression. So the generating function for the signed partition is actually a modular form. And in fact, many of the Mach theta functions written down in, by Ramanujan has this kind of relation to various combinatoric problems. It's kind of amusing to see. And another example I write down is, again, a function that you can simply write down in this, well, apart from this 1 over eta to the cubed prefactor, they also takes, you can express it in a sort of hypergeometric kind of way, and then it will turn out to be a modular form. And when you write down its Fourier developments, and what you see is, okay, the coefficients grow, and they're nice positive integers apart from this -1, this black sheep. And then the interesting thing is that all these numbers, 45 to 31 and so on, they actually are dimensions of reducible representations of material 24. So this is yet another one of the 26 sporadic groups, and the number of elements, the size is not as astronomical, but it's also pretty huge. It's about 10 to the 8. So that is our modular form that is observed to have a relation to the material group M24. And in fact, this observation that's made by Kuchi and Petrova and Auguri will turn out to be like the starting point of what's known to be moonshine later. So in moonshine, this function will actually be associated to the 24 copies of A1 root systems, funnily enough. And I hope I'm going to explain to you what the story here is. Okay, so before explaining the moonshine story, let me tell you what these things are about. Okay, so let's start by recalling theorem by Nima in the 70s and saying, like, okay, there are just 24 inequivalent lattices that are of rank 24 and are unimodular and have definite signatures. So one of them is the Leech lattice, which famously gives the optimal sphere packing in 24 dimensions. And it has no root systems. And then the rest 23, we will call them the Niemeyer lattices. They are uniquely labeled by their root systems. And their root systems are simply laced, and then subsequently I can define for you for each of these 23 Niemeyer lattices a finite group that I'll call G of X, where X is the root system. So, which is given by the automorphism group of the lattice, and modded by the boring part, let's say, that's given by the wild group of reflection with respect to these roots. For instance, if you take the case where like the root system is 24 of A1, then indeed the corresponding group is nothing but M24, M24 that we just that we have just seen in the previous slide. So now I can tell you roughly what the construction of moonshine is, and that's work together with Sean Duncan and Jeff Harvey. So we start with the Niemeyer lattice, and we can define from it, as we have seen, a finite group G of X. And on the side of modular forms, well, this ADU root system that's given by X, we can translate that into a way of like how the modularity of the function should be. And that together with the growth condition that we want the coefficients to grow slowly and not explode. And this is actually enough to lead to a unique function, just like in the case of the J function. So we can build a vector value modular form for each Niemeyer lattice in this way, okay, for each of the 23. And this construction can be generalized to associate a vector value modular form for each given element of the finite group that we have just defined earlier. Then the theorem says that then there exists, the theorem of Moonshine says that there exists an infinite dimensional module for this finite group that's again graded by some rationals here, and such that not just the dimension, but you can also build a generating function for the characters, for the G characters of each homogeneous component of this G module. And this will have the property that this is apart from this small correction or a wrinkle if you want. This is simply the modular form that you have built in this other way, for getting irrespective of the finite group. Okay, for instance, I mean, if you take X to be 24 copies of A1 and G to be identity, your construction will give you these this H function that I wrote down earlier, and indeed this is the generating function for the dimensions. Okay, because the G here would be the identity element, so the character is simply the dimensions of the homogeneous components. So there are two remarks here. The first is, okay, so there's a story I don't have time to go into, but the story of moonshine has a deep connection to the topology of K3 surfaces. Well, just for one thing, just give you a flavor of it, this H function I wrote down basically contains a completely equivalent information as the elliptic genus, which is, well, a loop space invariant, topological invariant, if you want, of free surface. Okay, so this is basically the elliptic genus that shows up in the moonshine function. So that holds a promise that this moonshine has a deeper connection to topology and other things, rather than just to find simple groups. And then the other remark is that it's been proven that there is such a module, and but this module has been constructed for only 8 out of 23 of the cases. So lots of mystery remains here. So I'm ready to move on to the next topic, but I don't think I have a lot of time left. But I'm just going to use maybe 3 to 5 minutes to tell you very briefly the relation between the appearance in modular forms and the study of free manifolds. Okay, so this is what I've been studying in recent years. So the questions and motivations from maybe the topology side is that what are the good topological invariants of free manifolds, which we can use to determine whether two free manifolds could possibly be topologically equivalent. And we have, for instance, the so-called Chern-Simons or Witten-Rishkin interval invariance, which is a function that defines the integers, which is these integers are the levels of the Chern-Simons, if you want. And is there also like a quantum Q-series invariance generalizing these Chern-Simons invariants, just like, you know, in the story of not polynomials, we have Q-series invariants, which we then hope to categorify in some way. So such a quantum invariance, we will, they're often called z-hats of M, has been proposed for specific families of three manifolds and starting with the recent work. Okay. So this, in particular, it's been proposed for the so-called plumb manifolds, and without going into any details, the data characterizing such a plumb manifold is a weighted graph, namely a graph with an integer associated to each of the vertices. And what's also important will be then the adjacency matrix of such a graph. Okay. And so the conjecture, well, or let me say, it's a conjectural statement that for all the plumb manifolds whose graph is like a 3-star graph, so, you know, just it can have many vertices on the legs, but only 3 legs, and which moreover has adjacency matrices that's positive definite, okay, that defines a positive definite norm. Then this quantum invariance would be a Mach modular form, or actually to be more precise, a Mach theta function of weight 1/2. And in particular, well, the Mach theta functions of Ramanujan, some of them do show up as a as a quantum invariance for 3 manifolds. I think that's something that I find quite amusing and surprising. So for instance, this very simple graph, which gives rise to the so-called Rieskorn sphere, if you know what it is, the Q invariance will turn out to be up to a simple overpowered Q, this Q hypergeometric series that I wrote down earlier. Okay. So and the evidence, there are some evidences for these conjectural statements, and there are some abstract arguments based on the relation to the Chern-Simons invariance and how such a Q invariance should behave, and so on. But the most direct evidence is that sometimes these plumb manifolds have other constructions, for instance, via the surgery of knots, of the complements of knots. And in that case, there are other definitions of these quantum invariants that you can employ to make calculations. Then you can check whether that fits with the, you know, let's say for the first 25 terms, the Q expansion fits what you expect it to be from this one point of view of this conjectural statement, and that works. So let me just say that we have seen that modular forms hold the secret of many, you know, mathematical objects in different corners of mathematics, and then I hope I show you that in the short decade and a half, after which the modular forms have been finally defined, it has also been showing up in, we have seen in combinatorics, and then I got no chance to tell you about how they appear in theoretical physics, but they also appear in a very meaningful and actually cute way in a study of, let's say, conformal field theory and string theory and so on. And it shows up in topology. It has a very interesting connection to finite group representations and so on. So I think the story will continue there about like what's there will be more applications and so on. And then in the other direction, we have seen like modular forms, generalized modular forms, and then after that there's some additional, some new structure that's even more loose that contains modular form as special cases, and then they have already been studied and showing up in these different areas, and I think that will be again a new chapter of like new mathematics and new applications on their part. So that finishes my talk today, and I apologize for the technical issues that was unexpected. So thank you very much.
Thanks very much, Miranda. I'll sort of applaud on behalf of everyone. And with apologies to the audience for the technical issues. These things happen. I'm very glad that we were able to continue. You can ask your questions through the Q&A function, and so Miranda can see them and answer them. Let me start off, Miranda. You mentioned that 8 of 23 examples were constructed. Now, so what is what holds you back to go further than that?
Well, yeah. So the problem is that these 8, the ways in which they're constructed sort of fall into 3 groups, and so there is, and none of these 3 methods seems to be readily generalizable to all cases. So we're still looking for, let's say, a unifying way to construct them like at once, and that I think still needs to be done. Yeah.
Okay. Does anyone else have a question for Miranda? So there's a question, from Alan Hall, Miranda. I don't know if you can read it yourself, but the question is, what is the difference between mock theta functions and just theta functions?
So I never defined what mock theta functions are. I defined for you what mock modular forms are. So mock theta functions are the mock modular forms whose shadows are theta functions. So indeed, there's theta functions there, but I mean, you put it on the side of shadow, and then so that's pretty indirect. I mean, shadows are called shadows are called shadows of mock modular forms because you can't really see them just by looking at mock modular forms themselves. So that's the relation between mock theta functions and theta functions. And actually, almost all the applications I talk about here involve mock theta functions, which are specific examples of modular forms, because mock theta functions have the nice properties that they have integral coefficients, while vast majorities of mock modular forms do not.
Right. Alan, did you have a follow-up to your question? Okay, thanks. So that answered Alan's question. Is there any other question? There's one by Gil Alon. As modular forms can be interpreted as k differential forms on modular surfaces, Is there a similar interpretation for mock modular forms?
Right. So the short answer is no. There are connections, relations between modular forms and modular surfaces, but in the end, they seem to somehow go through modular forms. It's yeah. In the end, it seems like it's always the sort of the modular piece that's connecting you to modular surfaces.
Okay, well, if there are no further questions, I'd like to thank you again so much, Miranda, and thanks for getting through the technical hiccups well, and being available all the way from Taiwan.
Sorry, Jan, there's one more question here from Satoshi Nawata.
Oh, I didn't see that.
It's in the chat.
Oh, okay. There's a chat question. Why does it have to be a 3-star plumbing graph to get modular forms?
Well, if you think about it, 3-star is sort of the simplest thing you can get, right? If you take out one leg, it will become just a line, right? So 3-star is the simplest thing. And there you already get relatively complicated things like modular forms. And you can ask, what if you add like a new leg to it? So I guess that's what you're asking, right? Oh yeah, that's exactly what you're. Then you get what's called the higher depth modular form, which can be defined in a recursive way. And then in more generally, I don't think there's any hope or any, like, more generally, if you consider general 3 manifolds, I think you won't just encounter such simple things, relatively simple things, such as mock modular forms. You will have to deal with general quantum modular forms, and there are beautiful stories there to be told, and are being told, I'm sure. But I mean, I focus on the mock modular piece because it's sort of clean and relatively simple, and understood, because there's a lot of this story about, you know, if you generalize it to multiple stars, and if you raise the rank of the gauge group, because what I'm talking about is the invariance for just the A1 case, the SU2 case, SU2, generalizing SU2 consignments, if you wish. If you consider higher rank consignments, and then you have higher rank stories, and things that do not have a name yet, but somehow fall into the general umbrella of quantum modular forms. I hope that answers the question, Satoshi.
There's a follow-up question, Miranda, on hyperbolic manifolds.
Can I show that? No, I personally cannot show that. I certainly believe that. But to prove it in generality, I think, I mean, at this moment, I think it's like a bit case by case, at the case by case. Well, case by case, not just manifold by manifold, maybe family by family, but kind of study. Just like, for instance, a family could be all 3-star graph plump manifolds. But a sweeping statement like that, I think nobody knows how to prove that right now.
Okay, thanks very much. And thanks very much, everyone, for attending the talk. In view of the time, we have to leave it at this. Thanks, Miranda, so much. Please join us next month with Australian fields medalist Akshay Venkatesh, in the next speaker in this online series. Thanks very much, everyone, for attending. Have a great day. Bye, everyone.
Thank you. Bye.